Greetings everyone. Greetings everyone. We are about to start our next session for the day. And for today we are going to have Dr. S. Ganga ma'am with us, Dean of R&D Department of CSC, BTech, MTech and PhD qualifications with her. So Dr. S. Ganga, working as Associate Professor in the Department of Computer Science Engineering at Cmrec Institute of Technology, Hyderabad, affiliated at JNU, Hyderabad. She holds PhD in Computer Science Engineering from Osmania University, Hyderabad. She has 11 years of industry experience in companies like HCL Technologies, Computer Associates, and in App Labs. She also has 8 years of teaching and research experience. She has completed many online certificates and courses related to latest technologies. She published extensively in national, international journals and conferences, authored books, and published patents. She served various managerial roles and administrative roles during her tenure of industry and academics. Ma'am, I request you to please come on the dais. Good morning everyone. So today I will be teaching a topic on batch memory reduction and feature extraction. Okay. So before starting, okay. So just now I think you had a session on supervised learning, right? Machine learning. So can someone tell me what is supervised learning? Pardon me?
Data is
labeled.
And what trained data, trained model.
Yeah.
And predict the output. And
Predict the model. Okay. So actually, you all know what is supervising machine learning. There are basically two types. You have other types also. But basically supervised and unsupervised learning. So in supervised learning, you make the machine learn from the labeled data set. Right? Labeled data. What do you mean by labeled data? What do you mean by labeled data? Yes? Yeah, you know what is the input, what are the features, and what is the corresponding output, right? So, for example, if you have how do we go back? You select any color. I want to go back, sir. Yeah. Okay. So basically, in I thought I like to select some color now. Right sir. Mark. So in label data, you have something like this, right? You have your data, you have all your features, and you have some input, right? These are all the features, right? These are all the features, and these are your labels. What do you mean by label? Label is nothing but some output that you are expecting.
the machine learning model. And you are also giving, you have some data where you have all the details of the student, the corresponding details, and whether the student is going to pass or fail. Okay. So you have some hundreds of students data. So this is all your input, right? You have 100 students data. So based on this data, based on what type of marks students have got, the machine learning model is going to learn whether the student is going to pass or fail. So based on this, what happens? When a new data, when a new student information is given, you can predict whether the student is going to pass or fail. Right? The machine learning model is going to learn the features. So it is going to learn from these input features. These are all your input features, right? The machine learning model will learn the patterns. What do you mean by learning from the features? It is going to understand the patterns that are there in the data, so that it can apply those patterns to the new data and it is going to give the output. Right? So this is what is a general machine learning model. Right? So in fact, you have supervised learning where all the input features are known and the corresponding output is also known. So what? In supervised learning, what happens? You learn a function which is given to the input to map to the output. Right? You learn in a supervised learning, you have your input, you map that you are trying to find a function which is going to map your input to your output. Okay? That is what is supervised learning. Because you already know the output. Whereas in unsupervised learning, you don't have this output, you don't have these labels. Right? This labeled data is not there. Based on whatever data is existing, you want to group them. Right? In class, like clustering or any other technique. What in unsupervised learning, what you can do is you can only perform some grouping, right? Based on some similarities that are there within the data. So that is what is in unsupervised learning. Because you cannot, there is no output. So you cannot map your input to your output. That's why you cannot perform any, you cannot identify any function that is going to map your input to your output. Right? So in unsupervised learning, you can only perform some grouping of the data based on how similar, based on the similarity features. Right? Similarity means whether how much is the distance matrix, or you use different metrics. Based on that, you are going to find the similarities and group them. So all these are basically depending on your features. So in whether it is unsupervised learning or supervised learning, machine learning is dealing with your features. Right? So you understand what are the features, right? So coming to what are the features. So from this example you must have learned what is the meaning of feature, right? So features are nothing but what are features versus labels. So you will understand what are features. That's what I have explained to you, right? What are the features. So if you take student example, you have all the details of the student, like student roll number, name, marks in each and every subject, how many hours of study he is doing, what time a student wakes up, what is his age. There could be so much of data, right? All this form your input features, okay? And labels are nothing but your output values, okay? From your input, what is your corresponding output? That is your label, okay? So features are the input variables describing the data. That is nothing but to describe the data. They are called as attributes. Another name for features is attributes, okay? These attributes or the features describe the characteristics of the data, okay? And the labels are nothing but the output variables the model learns to predict, okay? What is the model learning, okay? So what is it trying to predict? That becomes your output. Whether the student is going to pass or fail, that is your output. Or if you take any other example, like for example, weather prediction. You are in everyday life, you are seeing what is the weather, whether it is going to rain, whether it is going to be hot, sunny, okay? How is the weather? You are predicting. So what are the different types of values your output variable can take? They are called as the labels, okay? So this is features are the ingredients and the label is the dish, right? What input you are giving. If you take the example of a dish also, what are the ingredients that you put in order to make a dish? The output is nothing but your label, okay? Example, size, color, age are used to predict the label like dog or price. Depending on, like if you are given an image data set, okay? You want to predict what is the, which picture is that? Is it a picture of some animal or which animal it is? Okay, you want to predict. So that becomes what are the fields? So the input is the pictures of the various animals, and your output is the name of the animal that you are going to predict. Okay. So in supervised learning, features are the inputs and the label is your output, right? So now coming to the types of features. Okay, you need to understand what are the different types, different applications. There are so many applications your machine learning you are able to apply, right? So different applications may have different types of features. Okay, so coming to the different types of text features. So wherever you are having some NLP, where you want to apply some NLP, like for example, every day you are using Gmail, right? You are getting automatically some text is coming, some recommendations are coming, right? These are all based on some text processing. So when you go for text-based features, you use some bag of words. There are different techniques which are used to get the features from the text, right? A machine cannot understand text, right? Can it understand text? What? So it cannot understand. You have to convert the text into a form that the machine can understand. Okay? So you are going to convert the text, the letters or the words, sentences, everything are converted into a form which a machine can understand. These are different techniques. Okay, like bag of words, here, idea, photo. We are not going to learn about those things, but there are different techniques that you can use where you convert your text into a form that a machine can understand. They are called as embeddings. Okay. So, like examples of applications where you use this text features are sentiment analysis. You want to develop chatbots. All these are the examples of your text-based. All these applications make use of text-based features. Okay. So we will understand from the point of features. What are the features? Okay. So coming to the image features. Like for example, just now I was telling you are given some set of 1,000 images of various animals, and you want to predict which animal is there, which animal is there in that particular picture. So for that also the machine has to understand the features. So what are the different types of features for an image? They will differ from the image features of a text. Okay. So for different types of data, you may have different types of features. Okay. For image, you may have some histogram of oriented gradients, scale invariant features. Okay. Cmrec. So all these are used in order for the facial recognition application. You know what is facial recognition, right? Your mobile is able to identify your face, right? How is it able to identify? Okay, because it is learning your face. Okay, what are the features in your face? Okay, so there are different techniques which are used to identify the facial features. Okay, so these are all your image related features, image data. When it comes to audio, even audio also you have various applications like voice assistant, speech to text, right? You are talking at your system, like for in your ChatGPT or your Google, you can also talk, right? You can text, you can just read out the text and it is able to type. Right? So how is it identified? It is based on some signals, right? But the audio, how it is learning? It is learning some features. It is identifying the features of audio. So in voices, they use techniques like MFCC and other techniques. Okay. So we don't, based on what type of data you are going to work with. Okay. You may have to identify what techniques are required in order to get the features from that type of data. Okay. Why are we learning this is depending on what type of data you are going to work, right? You have to identify these techniques in order to get the features from that data. Okay, tabular features means just a table. Okay, the data is in the form of a table. Okay, this is any general like fraud detection, risk modeling, or anything, price detection. It could be most of the data is in this form, right? Time series data. What is time series data? It is varying with time. Okay, so like weather forecast, okay. Every hourly data is collected. So you get some time series data. Whichever data is based on the time or the data that you get from the IoT devices, the sensor devices. Okay. So these are all time-based, time series data that you get from these type of applications like stock market prediction, okay, forecasting or sensor data analytics. All these applications will have this time series data, and you use techniques like Fourier transform, lag features. There are different types of features that you identify. Okay, so these are all about features. Now, when you have these features, next is So we have done with types of features, right? So in real-time applications, you have for any type of data, you want to work with some type of data, there is huge amount of data. Okay? So if you are collecting the data, there could be multiple features. That data is described by multiple features. Okay? So do we have to use all the features in order to develop your application? In order to develop your machine learning model? It may not be necessary. Like for example, even if you take the student data itself, okay? Your student data, what I was saying, you have the student roll number, name, age, height, weight, okay, marks, and whether you are going to pass or fail. Do you think all the features are required for predicting the student whether the student is going to pass or fail? Do you think everything is required? Is that age is related to the whether the person is going to pass or fail, or the student is going to pass or fail?
No.
It is not related. So there is some unrelated data also. Okay, there could be unrelated data, or there could be some redundant data also. Redundant data means, like for example, you are having marks. Okay, there are marks in each subject, and there is also average marks. Okay, average marks means it is already having this marks data also, right? So if it is redundant, your average field, okay, in your student database data set, if you take, it is a redundant because already marks of each subject is there. Yes or no? So it is learning something. When you are giving all these details to the machine learning model, it may not try to learn the correct patterns. Okay? The correct function that you are trying to map from your input to your output, no? It may vary. Okay? So this is because of these problems, you have various problems with this high dimensional data. Well, in real time also, this is a small example what I was talking about your student data. But in real time, if you take some genes related data, or if you take your weather forecast data, there are so many features. Okay, there are so many features, and your machine learning model will not be able to learn all the features from all the features. It becomes very difficult. Because of this is called as curse of dimensionality. Okay, what do you mean by dimensions is the number of features. Okay, what do you mean by the dimensions of a data? It means the number of features that you are having in your data set. Okay, so as the dimensions increase, data becomes sparse. Okay, if you want to convert them into some machine readable form also, it becomes very sparse. You know, sparse matrix, right? So it has many zeros. Okay, so it becomes very big. Okay, the data becomes very big and reducing the model performance. When the data is very big, okay, there is some unnecessary information, unnecessary data is there, redundant data is there. It will lead to wrong predictions. Your application, your model that you are trying to build, it will not give correct predictions. Okay, the accuracy will be very, very low. Okay, so this is called as curse of dimensionality. Because curse of dimensionality means because the dimensions are more, the machine learning model is not able to learn properly. Okay, so that is how do we handle these problems of high dimensional data. Okay, so it can also lead to overfitting. So overfitting, the machine learning model is learning the noise also. So whatever noise is there. So noise, what do you mean by noise in the data? Like I was telling, right? Height, weight in the student database. Is it anywhere related to my whether the student is going to pass or fail? So that becomes noise. That is nothing but noise in the data. Unnecessary thing that is there in the data. Okay, that's leading to poor utilization. Because of learning, it noise, no, it will not. It is trying to give some importance to that noise also. Okay, when you are building a model to predict whether the student is going to pass or fail. Okay, and you are considering his height and weight also. It will give some importance to this height and weight also. So do you want it to give that? No, right? It should not give any importance for these type of features. So you have to remove these features, right? So how do we do that? We will be learning next. Okay, and high computational cost. Why high computational cost? If the data is very big, you need more computational power, right? Yes or no? You know what is computational power, right? How much memory is required, how much CPU is required in order to learn the patterns. The more the data, the more amount of time it is going to take to learn, right? And so more CPU and memory, right? So these are nothing but increased memory usage. real information. So difficulty in visualization and interpretation. When you have huge amount of data, it is very difficult to show it graphically. Okay, you cannot visualize in a picture. Pictorially, if you want to represent the data. Okay, if you want to say what are the different features, how my data looks like if I put it in a plot, if I want to plot it on a graph. Okay, so it doesn't fit and it becomes very clumsy and you will not be able to understand anything out of that. So why do we use this visualization actually? So that it gives you some insights, right? So that you can understand what this picture means like. If the bar is big or small, you take some insights from that, right? Yes or no? If the picture is very clumsy, you can't get any information out of that. So because when the data is more, these are the difficulties that you face with high dimensional data. Okay? So now we have to reduce this. Okay? So you have very huge number of dimensions of data. We have to reduce that. Okay? So different types of dimensionality reduction techniques are there. Okay? Basically there are two methods for reducing the dimensionality. There are feature selection and feature extraction. Okay? Feature selection is different. Generally in outside, many people will get confusion between what is feature selection, what is feature extraction. They are completely different. Okay? Feature selection means out of the k dimensions, if your data set is having k dimensions, that capture the maximum available, finding the k dimension that capture the maximum available information and discarding the remaining dimensions. So for example, if our student data, what we were talking, right? So you can select only what is required and you remove the dimensions, like you remove your average and your height and weight of the student is there, or the name of the student is there. There is nothing related to your model, right? So you remove them. Okay? You directly remove those attributes from your data set. Okay? That is when you are pre-processing your data. Okay? During the pre-processing phase, you remove these attributes from the data set. Okay? That is called as feature selection. In feature selection also we have different types. We'll look into that. But to understand what is feature selection, right? Yes, you are going to remove some of the attributes from your data set, okay, which are not required, which you feel that it does not contribute to my model, machine learning model. Then you remove those features, okay. Next is feature extraction or projection method, okay. So here, this is basically used when you really have huge amount of data, huge dimensions of the data. In this, what you are going to do is you are going to transform the existing text. Here what is that you are finding a new set of dimensions. Okay? You have some d-dimensional data and you are coming from d-dimensional data to some k-dimensional data. That is you are converting, you are transforming this data. That means all the features that are there in your data set, you think that you cannot remove them. Okay? In feature selection what we were doing, we thought that we can remove them and we could delete some of them. But we cannot do that here. Okay? You have huge amount of data and you think that everything is important. Or everything is important in some way. Everything contributes to your model. But your learning is very difficult. Okay, it is occupying so much of computation. It is very difficult for training the model using so much of dimensions of the data. Then what you can do is you can transform this d-dimensional data into some k-dimensional data. You are reducing. Ensuring at the same time you ensure that all the information that was there in this d-dimensional data is also there in your k-dimensional data. That is called as feature extraction or projection method. How do you do that? I will explain you next. Okay? So finding a new set of k-dimensions from the combinations of the original d-dimension. Okay? You are trying to find. So there is, once you do this feature extraction, you will not have the same input features that you had in your actual data set. Okay? You are transforming them. Okay? So example of there are different techniques for this feature extraction, like PCA, that is nothing but principal component analysis, independent component analysis, and linear discriminant analysis. There are many others also. Okay, these are some of them. Okay, so this PCA is generally used for unsupervised projection method, and this LDA is used for supervised linear discriminant analysis. Okay, our main goal here today we will be learning about PCA. Okay, one of the techniques, and the other techniques also work in similar lines. Okay, but the technique may be different. Okay, so see the main difference here, feature selection. You have the original input features. Okay, these are the so many features. From this, you are selecting some three. Okay, that is feature selection. What is feature extraction? You have your original input feature. You are going to create features through some combination. New features. Okay, this is nothing but feature extraction. Clear, everyone? Clear? Any doubts? No doubts? Either you are following or you are not following. Following? Okay. Coming to the types of feature selection. Okay. So feature selection, what is it? In feature selection, you are directly discarding some of the features. Okay. In that also you have different methods like filter method, wrapper method, embedding method. Okay. In filter method, we select features using statistical measures. So how to decide? See, student data, you know that student height and weight does not contribute to your model and you are directly deleting because you have some domain knowledge there. But you don't know, like weather forecast, you get so much of data. You don't know which one to remove. Okay, how do you remove? Okay, so you have to follow some, you have to use some statistical measures. Okay, like correlation, chi-square, information gain. These are the different measures that can be used to remove some of the attributes from your data set. Okay, so that is one way, filter method. Okay, wrapper method, you use a machine learning model to evaluate the feature subsets. And what you do is you select some machine learning model, okay, and you start training that model with some one feature. Okay, how it is, how is it behaving, you test. You select next two features. You keep on adding some features and you come up with some model to decide which features are important. Okay, you start like randomly you can do that. Okay, different like forward selection, backward elimination. Or forward selection is you go on adding features and try to see how the machine learning model is behaving. Okay, and you see that some attribute there is no difference in the model performance, then you can remove that attribute. And backward elimination is you initially start with all the features and go on removing one feature to see how the model is performing. And you can know, right, by doing so many iterations, you can know which features are important and which features are not important. Okay. Similarly, embedding methods, these perform feature selection during model training. During model training only you select which are required and which are not required. Okay. A landscape, decision tree, random forest. You use different, how you are selecting the machine learning model, and that time only you are going to select which features you are going to use for your model. Okay. Coming to your feature extraction. So that was feature selection method, right? Coming to your feature extraction methods. These are the different methods that I was saying, right? PCA works on the concept of maximum variance. Okay. So maximum variance means how the data is distributed. The maximum variance has to be captured in your principal components. Okay. So you have your dimensions, right? Okay, so you have your, you see the next slide to understand this. It focuses on having maximum variance. Okay, what do you mean by maximum variance? I will explain you, don't worry. So it reduces correlated features while preserving maximum variance. What do you mean by correlated features? Like I said, I told you, right? You have marks in each subject and you have your average also. They are both related. Yes or no? They are related. So they are correlated. So you try to remove the correlations. Okay? Whatever correlations are there, you try to remove them and you keep only your variance, how the data is varying. Okay? So these are basically, it is used in image data and gene data. Genetical data is there, right? So those type of data. LDA is maximizes class separability. Okay? Enhances class separation for the classification task. So here in LDA, what it does is it focuses on separating the classes. That means all the classes which belong to the same class, all the data points that belong to the same class are grouped into That is what is LDA does. Okay. Auto-encoders are used in text data. Okay, when you have text data, they are nothing but they use neural network based technique. It is auto-encoders. They use a neural network based technique, and they are helpful in understanding the features or reducing the features in your text data. Okay, this is neural network based feature learning. Learn compared to latent retrieval deep learning. So when you want to apply deep learning for text based data, these auto-encoders are used. Okay, which will help you learning the important features in your data. Okay, so they are neural network based. They are built on neural networks, and they help you in learning the text based important features of the text. Okay. TSNE is there is TSNE and UMAP. TSNE means T-distributed stochastic neighbor remedy. Okay, and UMAP is uniform manifold approximation and projection. These two methods are used in non-linear data. So when generally PCA is used for linear data. That means there is linear relationship between the attributes in your data. Then only PCA can be used. Okay. If you are having non-linear data, then you have to use this TSNE and UMAP. Okay. What they do is they want to convert this non-linear data into some linear data. Okay. And then so these are visualization. Basically, these two methods are used for visualization. Okay. When you have your visualize this high-dimensional data, you can use this TSNE and UMAP. Okay. And CNNs are basically used for images. Okay. So when you are working with image data, you can use CNN in order to identify the important features from the data, from the image data. Okay. CNNs automatically for images, they are highlighted features for image and visual tasks. Okay. Then image tag. What is image tag? Images. You give an image. Okay. You give a to your model. Tell you it is going to give a text message. What is there in that image? Okay. If there is a garden with one boy playing in the garden, that picture is given to the machine learning model, okay, or the deep learning model. It is going to give a text message saying that what is there in that image. Okay, so it describes the image basically. Okay, or if you give like any person's image, like RPM Modi image, if you give, it will describe that is a picture of Narendra Modi. Okay, like that. So these are the various tools that are used in different types of data for dimensionality reduction. So now we will be learning about what is PCA. Okay, what is PCA? So what is PCA said? We are going to transform your d-dimensional data into some k-dimensional data. Okay, that is what is p-dimensional. You are reducing the number of dimensions. Okay, so for example, you have C. Here so many dimensions are there. Okay, this is your original data. Okay, your original data is described using so many dimensions. Okay, I want to remove the inconsistencies, redundant data, and we want to put together the highly correlated features. Okay, and come up with only few features. Okay, so here I could have some hundreds of features, and I want to come out with only some 10 features, and I want to these features can be minimized to 3 features. Okay, so new data space with lesser features that retain most of the information. So whatever information is conveyed by this data has to be conveyed by this data also. Okay, so that you have to ensure whenever you perform this PCA, what is your main goal is the knowledge retained. Whatever the knowledge was given by this data, it has to be retained in this data also. Even though you are trying to reduce the dimensions, you have to have all the information that was given by this has to be retained by this. Understood? This is the main goal of PCA. Okay. So PCA is a dimensional reduction technique that enables you to identify correlations and patterns in the data set. It will identify the correlations. Correlation with what? How this this particular attribute is correlated to this attribute. Are they related? If they are related, how much is the relation? Okay. Okay. Based on these two are related. I don't want these two. I want some other feature which will give the same information that was there in the previous two. Okay. Understood? Yes, following everyone? Okay. So it will understand it will help you enables you to identify the correlations and patterns in the data set so that it can be transformed into a new data set of significantly lower dimensions. Okay, this new data set is having lower number of attributes. Yes or no? Yes, you are transforming this high dimensional data into a lower dimensions data. Okay, without loss of any important information. Okay, when you are converting this high dimensional data into a lower dimensional data, you should not lose any information. This is very, very important. Okay. Next. So, this is a linear dimensional reduction data algorithm. What do you mean by that? It can be applied for linear data. Okay. Where the data set should have linear attributes. Okay. Then only you can apply this PC. Okay. It transforms your data from high dimensional space to a lower dimensional space. So, for example, in gene, I was saying, right, in genetic data or the biological related data sets, if you take, there will be huge number of dimensions. Okay, hundreds and thousands of dimensions will be. Say, for example, this data set, which is related to some genes. Okay, it has 10,000 genes. Okay, these are the different features. Okay, I want to convert these 10,000 genes into some 15 principal components. Okay, that means I am having my dimensions in my original data set is 10,000 features are there. Okay, I want to reduce it to some 50 features. Okay, so it can be by applying PCR, I can convert this to this. Okay, so a principal component summarizes the most important patterns or variations in the data. So what are we saying that these are called as principal components, right? So these are called as you are converting this 10,000 to 50 principal components. The dimensions in the new data set, they are called as principal components. Don't get confused. What do you mean by principal components? The transformed attributes. Okay, whatever your original data set is there, from that you are transforming into a new set of attributes, right? They are nothing but your principal components. Okay, they are nothing different. Okay, the transformed, whatever the transformation you are doing, okay, by from this 10,000 genes and coming to 50 principal components. Okay, and this 50 principal components should give me all the information that was there in my 50,000 using my 50,000 attributes. Okay. So a principal component summarizes the most important patterns or variations in the data. So what it does actually is, okay, it will capture the variation. Okay, what do you mean by variation? Okay, I will explain this. Say for example, okay, you had you had the data in this way. Okay, you had some two. Say that I had only x1 and x2 features are there. Okay, say I have only two features and all my data is like this. Okay, all my data is in this way. Okay, one data point is here, one data point is here, one data point here, like this. Okay, when I am having two features, I can draw it like this in two-dimensional space. Yes or no? Yes, I can represent my two-dimensional data. I have only two features, x1 and x2, and how they are related, I can draw in this way. Yes or no? Okay, so this is representing my data in two-dimensional space. So from this, what is the variation in x? Okay, from which value of x to which value of x it is varying. That is what is variation in x. Yes or no? So what is the to here. This is your variation in x1. Yes or no? And what is the variation in x2? X2 variation is from here to here. This is my variation in x2. Yes or no? So what I do is, if I am having such type of data, I can transform this data by moving this into I can draw a line like this. Yes or no? Okay? And I map this into this direction. Okay? So if I transform this x1 onto this axis, okay? I rotate my x1 using this theta. Okay? Using this theta. Okay? What happens? This line will become like this, and what will happen to this line? What will happen to x2? It will move here like this. Yes or no? So when you transform it like this, your data will get transformed. Okay? How it will get transformed? It will come in this way. Your data will become like this. Right? Yes or no? The same thing if I transform, this will be your new Z1, Z2. Yes or no? Just imagine, okay? I am transforming this x1 into your Z1, and this is your Z2. If I draw my Z1 and Z2 in 2D, all the data points will come in this way. Yes or no? Following? Understanding? They will come in this way. Right? So now what is the variation in Z1? This is my variation in Z1. And what is the variation in Z2? It has become very small, very negligible. You can even neglect this. And all your information can be represented using Z1. Understood? If you are taking, why I am saying this? By transforming from my two-dimensional data into one-dimensional data, I am able to retain my maximum information. I can only use my Z1 and I can do my prediction. I don't need again x1 and x2. In place of x1, x2, I will replace them with Z1. Okay? So this is the advantage. So all the information that was there is still here in Z1. Right? This is the variation. So this variance we are able to capture in your principal components. Okay? That is the main important concept behind PC. Okay? You are able to capture the maximum variance in your data into your principal components. Followed? This is very important. Okay? Okay. So, it summarizes the most important factors of variations in the data. Right? In a single cell RNA sequence data, thousands of genes. So that's what I was showing, right? There are thousands of genes. Each piece PC assigns a loading score to every gene. Okay? Loading can be positive. That means when you are transforming, right? This x1, x2 I have transformed into z1, z2. Right? So this z1 can have different values. Okay? Some positive values, some negative values, some zeros. Okay? How they are contributing to. Okay? Based on how they are contributing, it can have positive, negative. Larger contributed values indicate greater contribution. Okay? The larger values, if you go, that means they are contributing more to your feature. Okay? That feature contributes more. Okay? That particular dimension contributes more. Okay? So not all genes are equally informative. So if you take the genes data only also, all the genes may not be important, right? Like how I said about student, all the features are not important. Some genes vary significantly across cells and others show minimal change and contribute less. Right? So this is about how does it do? So you are transforming. So I have given you the example, right? What are we trying to do? We are transforming the axis from one axis to the other axis. Okay? So are the new axis directions in the data that capture the biggest differences between the cells. Okay? What are the differences among the different attributes? These principal components are able to capture that differences. Okay? The biggest differences between the cells. These directions are chosen so that, okay, based on whatever directions you are changing, those directions will capture the maximum information. Okay? The first principle, so in that data can show you the maximum. Like that you can have hundreds of features, right? And I am trying to reduce from 100 features to 5 features. That means there are so many pieces. It is not only one PC one, right? You can have principal component 1, 2, 3 and 4 and 5. Right? When I am reducing based on the number of dimensions I am converting, you can have different number of pieces. And each PC, each principal component will capture different information. Okay? The first PC will capture the maximum information. The second PC will capture the next level of information which was not captured by PC1. There will not be any duplication. Okay? That's how the PCA will work. Okay? To ensure that the maximum variance in the data is captured by PC1 and the next variation which is not captured by PC1 is captured in PC2. And the next variation which is not captured by PC1 and PC2 will be captured in PC3 and so on. Okay? So the principal components capture the biggest differences between the cells. So these are your cells, right? These are the cells, these are your genes. So among this, whatever the biggest differences are there, they are captured by the principal component. So you see here, the variation, that's what I was saying, right? Each PC captures different type of information. And PC1 will capture the maximum amount of variation in the data. And okay. So PC1 captures the maximum variation. Hello?
Back down. No problem.
So PC1 captures the maximum variance, okay? And PC2 the next maximum variance. In that way, if you are converting from n-dimensional data to d-dimensional data, there are d PCs, d principal components, right? The first principal component will capture the maximum variance and it goes on in the decreasing order. Okay? The variance extent will be in the decreasing order in the principal components. Okay? So the principal components are ranked and orthogonal, independent from each other. What do you mean by orthogonal? They are independent. Each PC is dependent, is different. There will not be any overlapping of the information among the PCs. Okay? So one PC is in one direction, the other one will be orthogonal to that. That means the data captured or the knowledge captured in one PC is completely different from the knowledge captured by the other PC. Understood? So principal components are ranked. Ranking means because PC1 is capturing most variation, PC2 is capturing the next level, PC3 goes on in the decreasing order. Okay? So in any machine learning model that you are applying PCA, the first few PCs, okay, will capture the maximum 95% of the variation in the data. So the 95% of the knowledge that is there from your data you can get it from the first few principal components. Okay? So this variation is decreasing, that's why it is ranked, and orthogonal because there is no duplication of any information in the different principal components. Following everyone? Yes, are you able to hear last page? Yes? So here, see for example you have your PC1 here, okay? It could capture some types of cell division, okay? And it is focusing more on these aspects. It is giving some positive values for these type of genes, okay? If you take this example, okay, our gene data example, you have some cells or some genes which are capturing this particular data. That's why it is giving more value, okay, for these genes. It gives some negative values for certain genes. It gives some particular genes. It is giving some very, very low values for this type of genes. Okay. So based on how the principal component is learning is based on each cell. For each cell, it is going to give some values. That is how the principal component is formed. Okay. So PC1 captures the highest variability in the data set. From your data set, the maximum variance. Okay. What do you mean by the maximum variance? I've shown you in the diagram, right? The maximum variance is captured by the principal component 1, the first principal component. Okay. That is, genes promoting cell division have high positive scores and genes linked to. This is example from the genes data set. Okay. For what type of genes it is giving more importance or high values. Okay. And so PC1 summarizes cell proliferation. Some aspect of the data is summarized by the PC1. The most important aspect. Okay, it could be cell proliferation. This is with respect to this data. Okay, nothing to do with our PCA. Okay, so high PCA, PC1 is dividing the cells, and low PC1 is not. Low PC1 indicates that it is something related to some dying cells. Okay, genes related to some dying cells. That is the example. Okay, so PC1 alone cannot separate healthy proliferation. So PC1 can capture maximum data, maximum variance, but it will not give you the complete information. That's why we have to go for other PCs also. Okay, we are not saying that PC1 alone, the first principal component alone, can give the all 100% data that was there in your original data set. Okay, so it is capturing some amount of data. Some things are not captured. That's why we have to go for other PCs. So PC2 captures the next highest variation. Okay, in your entire data set, whatever the variation is there. So PC1 is capturing to some extent. The next highest is captured by the PC2, and so on. Okay. So this is like this PC2 here in our example, it is capturing the immune function related to gene expression. Okay, some aspect of genes it is capturing. Okay, which was not captured by PC2. Okay. So gene patterns in PC2, highest PC2 scores are given to immune response. What happened? So combining both PC1 and PC2, you get the maximum variance is captured. The maximum variation in the data is captured by combining both PC1 and PC2. Okay? So here you see here, okay, this is something called as screen plot. This screen plot will show you the plotting of the various principal components. How much is the variance captured by each PC? Okay, you see here PC1 captures. Sorry. Okay, your PC1 captures the maximum variance, around 73% of the variance in your actual data set was captured by PC1. Okay, let's say PC2, it is capturing around 25% or 28%. Okay, PC3 low. Okay, so like this screen plot is used for capturing the indicates how much variance information each PC holds. So this PC is holding me 73% of the knowledge from your original data set can be given to PC1. Okay, and so on. Understood? So real data sets. Okay, when you want to apply this in practice, okay.
Babu, last rows, don't talk.
The data is very, very complex. Okay? In real time, the real data sets are complex and very few pieces are often insufficient. Okay? So depending on how your data is, okay, how much is the variance in your data set? Based on that, you have to decide. You cannot decide that for this particular, for any data set, 5 pieces are enough, or if you are having 1000 dimensions, you need 10 dimensions. There is no hard and fast rule. Okay? It all depends on the data. It all depends on the data. It all depends on how much is the variance in the data. Okay? What is the relationship between the different attributes in the data? You can have different number of dimensions or principal components. Okay? So more pieces are needed to distinguish similar cell types and subtypes. Typically 30 to 100 pieces are computed. Okay? So because our data was having how many genes? 10,000 genes, right? So nearly at least 30 to 100 pieces are required if you want to capture that 10,000 genes data. Okay? Screen plots show how variance is distributed. Okay? PC many pieces. Too many dimensions to visualize use. So this is all the high dimensions, right? 30 to 100 pieces is not a small dimension, and you can't represent that also using the normal visualization. If you want to do, you cannot do, right? Only up to 2 dimensions or max 3 dimensions you can visualize up to 3D. Can you visualize 4D, 5D dimensions? You cannot, right? For that you use this PSNE or UMAP. Okay? These are used for high dimensional data. So how? PCA works. Okay, how PCA works? Here we see how do we calculate? Okay, how the PCA is going to reduce the dimensions. Okay, so till now, why PCA is required? Okay, but how does it work? What are the steps involved in the working of the PCA builder? Okay, so PCA uses linear algebra to transform data into new features called principal components. So here you are going to use linear algebra. Okay, here please. It finds these by calculating eigenvectors and eigenvalues from the covariance matrix. I think everyone knows there. You have learned the linear algebra, you know what are matrices, you know what is a covariance matrix, okay, mean, standard deviation, covariance, variance, covariance. Yes, all these formulas you must have learned, right? So all that we are going to use to in the working of the PCA. Okay. So PCA selects the top components with the highest eigenvalues and projects the data into the to simplify the data. So whatever, how are you going to calculate these eigenvectors and eigenvalues? Okay. Eigenvectors are nothing but the directions. We said that we are transforming the direction. We are shifting the axis, right? Yes or no? We are shifting the axis of the dimensions of the attributes. So that is given by the eigenvectors. And the values of the PCs are given by the eigenvalues. Okay? So first step is standardize the data. Okay? You have your data. Okay? Or you have to standardize this. What do you mean by standardize? Why do we need standardize? Because you have different types of data. Okay? Some data may have single or values from 1 to 10 only, range values from 1 to 10. Some data may have higher values, 100, 200, 30. So there is so much of difference among the values of the data. Okay? Different attributes may have different types of values. So you have to bring all the values into a standard form. For that we do this standardization. How we do this standardization is, you may have data like this. Some rating is there. Rating has values just 1, 2, 3, 4, 5, right? Which is a single digit number. Whereas number of downloads, if you see, these are having high values. Okay? There is so much of difference among the data. If you use the same data directly in order to do the dimensional prediction, it will not give you correct results. You have to, all the data has to be in some standard form. Into some standard form. So you convert this into standard form using this formula. Okay? Z equal to variable value minus mean by standard deviation. Okay? Using this formula, you standardize your data into the, so that the output of this will be what? All this data, your ratings, your number of downloads will be in the same form. Will come to the same form. Okay? So standardization is all about scaling your data in such a way that all the variables and their values lie in the similar range. Okay? You are bringing all the attributes into the same range. Okay? That is what is standardization. Next step is finding the covariance. What do you mean by covariance? That this covariance matrix, you are trying to find the covariance matrix. This covariance matrix will show you what is the relationship between each and every attribute. Okay? So what is the main goal in PCS? Maximum variance we want to capture. Right? The maximum variance in the data we have to capture. So that how we can do? Only by checking what is the correlation between the attributes. Okay? So that you have to find using D by D dimensions. Okay, D cross D dimensions. Because from every attribute, how much is the relation with the every other attribute in the data set, right? That you will get it using your covariance matrix. So I showed you a diagram. See, something like this. If you have two attributes, okay, A and B are the two attributes. Then you calculate what is the covariance between A to A, A to B, B to A, B to B. Okay, so this becomes a covariance matrix which will show, which expresses the correlation between the different variables in the data set. It is essential to identify heavily dependent variables because they contain bias and redundant information. Okay, so the correlation is high means they are very much related, right? They are very much related. So the covariance value denotes how codependent two variables are, right? How codependent. What is the relation between those two attributes? Negative covariance indirectly proportional. Positive covariance directly proportional. Now what do you mean by that? So if direct correlation is if you increase the value of A, value of B also increases. Okay? Indirect means inversely proportional. If the value of A increases, value of B decreases. Indirect. So that is represented using your, you get all the relationships, right? When you are having D dimensions, a D by D matrix will give you the entire relationships. You will get the entire relationships among your attributes using your covariance matrix. Yes, followed? After this, you find the principal components. How are you finding the principal components? By calculating the eigenvector and the eigenvalues. Okay? How do you do that? I'll tell you. So you use this Ax equal to, okay, here. So principal components are the new set of variables that are obtained from the initial set of variables. From the initial variables, we are trying to find the principal components. Okay, they are also variables only, right? So they compress and process most of the useful information, this data. So how are we finding them? Using your eigenvectors and eigenvalues. Eigenvectors are those vectors where the linear transformation is performed on them, then their direction does not change. Okay? So, for example, that's what we have seen, right? So when I am transforming my x1, okay? When I am transforming my x1, the direction is not changed, right? It is only shifting the axis. Okay? The direction of the vector is not changed. Right? Yes or no? So there is no change in the direction. Eigenvectors are those vectors where the linear transformation is performed on them, then their direction does not change. Okay? And eigenvalues simply denote the scalars. Scalars means how much is the difference? Okay? What is the difference between these? How much is the distance between the values? Okay? To the axis. That is denoted by the eigenvalues. Okay? So eigenvectors and the eigenvalues are mathematical constructs that must be computed from the covariance matrix in order to determine the principal components. From the covariance matrix, you are going to calculate the eigenvalues and eigenvectors. Okay? Using what? Using this. How are you going to calculate that? Using this Ax equal to lambda x. Okay, this is a relationship that you have between your eigenvectors and eigenvalues, and from this your eigenvalues are represented by the lambda. Okay, and then you calculate by. Actually, I have one example also, solved example if you want, or I can share that example. You can do it. Time is up. Okay. So once we calculate that, okay, once we calculate the eigenvalues, you have to calculate. You have to find the principal components, right? What will be the principal component? The highest values. Okay, you have to order the eigenvalues into the in the descending way. Okay, you have to arrange the eigenvalues in descending order and then select the top 4 or 5 or depending on how many you want to select. You are going to select so many principal components. Okay, so after calculating the eigenvalues and eigenvectors, PCA ranks them by the amount of information. Okay. So select the top k component will capture the most weighted like 95%. Okay. The top 4 PCs will be capturing the 95% of the information from the original data set. Okay. Transform the original data set by projecting it onto the top component. This means we reduce the number of features while keeping the important patterns in the data. Yes or no? Understood? So you see that this is the variance, right? PC1 component, PC2 component, direction of the most variance, second most variation. This is the direction of the first most variance, right? Okay. PC1 is the most significant and stores the maximum possible information. PC2 is the second most significant and stores maximum information and so on, right? So this is the computing. Once we have computed eigenvectors and eigenvalues, we have to order them in the descending order, where the eigenvector is the highest eigenvalue, is the most significant, and thus comes up with the first principal formula. Yes? So this is what it is. So this is the variance shown by this PC1, and this one is the variance that is shown by the PC2. By transforming your one of the original attribute to the next axis, to the new value, new axis. So advantage of PCM, collinearity handling. It is able to handle all the relations among the attributes, right? So create new uncorrelated variables. By identifying the correlation between the variables, it is trying to find out new variables which are not related to each other, which are independent. Okay? To address the issues where original features are highly correlated. So it is able to handle this multi-collinearity. Noise reduction, right? Eliminates components with low variance, enhance data clarity. So the noise is removed. It is not required and you have to remove it. Okay? Data compression represents the data with fewer components, reducing storage. Yes? When you are converting your high-level data into your physical components, you are reducing the size of the data. So it automatically is doing the data compression. Outlier detection identifies unusual data points by showing which ones deviate significantly in the user space. Okay? Disadvantages. There are some disadvantages also. When you are trying to scale, okay? Here please, just 2 minutes. Diagnosis. Like interpretation challenges. So we are transforming your original data into principal components. But do you know how much each PC1 or what exactly is captured in the PC1 variable? You cannot tell. It is coming based on some calculations. It is coming out as a new PC. But you really don't know how much value each attribute is contributing to your actual machine learning model. And there could be some information loss if it is not handled properly. Okay? And linearity. You need linear data. Then only you can apply PCA. Okay? For non-linear data, you have another one, kernel PCA. Okay? Kernel PCA, what it does is it is going to transform this non-linear data into linear data by using some kernel functions like radial basis function and other types. There are some functions using which you can convert your non-linear data into linear data. Yes. So computational complexity, because you are trying to convert your high-level data into lower dimensions. These lower dimensions also could be high. Okay? If they are high, then it will lead to more computation. Risk of overfitting also could be there, because it is trying to fit the maximum variables into fewer variables. There could be problem of overfitting also. But in kernel PCA, right? It uses different kernel functions to transform your high-dimensional data into lower dimensions. Actually, I also wanted to show some examples. If you have any queries, mom, Indian silence, last. No, actually, just if you want, just listen. For explanation, for implementation. For implementation, you all know in machine learning, for generally in any machine learning model or deep learning model, everything is already existing. What you need to know is how do I do that? Okay, you need to know that there is some PCA which I can use and I can apply to my data so that it reduces the number of the complexity with the data, right? You want to reduce the dimensions. Then how do you do that? Okay. So you have like in pre-processing a scalar, not pre-processing, you have the standard scalar. Using this standard scalar, you can scale your data. That means you are converting all the attributes into the same format, into the standard format. Once you do that, you can apply PCA. Okay, PCA is implemented in this scalar decomposition. Okay, directly you have this PCA. Okay, you can just copy. Once you do the scalar, say for example, you have your data like this. So if you have your data like this, okay, there are 4 attributes. Okay. So you have your data and say you want to determine the gender based on some